It's question show day. Your questions, my answers, wherever you are on my channel. If a question pops in your brain, just go to any video, just type in your question. I will gather a bunch of them up and I will answer them here. As always, I've got as mostly, I've got another guest answerer today, Dr. Sabine Hossenfelder, who wrote the book Lost in Math and answers a question about quantum mechanics. So let's get into it. Keith in ADHD. Once the sun engulfs a chunk of the solar system and shrinks down again, is there a chance new planets could form from the remains? So what you're talking about here is this idea of the sun dying at the end of its life, that it turns into burns up all the fuel in its core, turns up into a red giant star, sloughs off all of its outer layers, and then compacts down into a white dwarf star, which is like a gigantic diamond. And then it will cool down over hundreds of millions, billions, trillions of years until it becomes the background temperature of the universe. And that is the ultimate fate of stars like our sun. And so the question is, what happens to the planets that are trapped around the stars? It goes through this entire process. Well, astronomers think that as the sun expands into a red giant, it's going to gobble up Mercury, Venus for sure, maybe the Earth, they're not entirely sure, but also it's going to kick off a lot of its mass and change the orbits of all of the rest of the planets. So they might orbit farther out, they might interact in ways that will kick each other outside. And actually, astronomers have found examples of white dwarf stars where they think they see debris left over after it's gone through this entire process. And the kind of thing that's interesting about that is that a white dwarf star actually still puts out a lot of heat. And if you're close into the star, you can gain temperature to live for a very long time. So if conditions were perfect, you can imagine some inner planets surviving after the star dies and those planets getting a second chance at life as the sun continues to cool down over a very long period of time. So we can't say it's total destruction, most likely, but it's sort of a really fascinating idea about what could be in the future of stars like our sun. Jeremy Weinrich. How can stars capable of collapsing into black holes possibly fight back against overwhelming gravity? Is their matter spread out over a large enough area that the force isn't strong enough to overcome fusion? So stars are the size that they are because they are in perfect balance. There is, of course, the gravity that is pulling everything inward, and that wants to turn the star into a white dwarf, right? Compact all of that matter down into just this tiny little ball where the limit is the bonds that, that atoms won't allow themselves to be packed any closer together. And so then the question is, what's the force that is pushing outward to counteract that inward force? And the answer is light. It's called light pressure. And so you've got the fusion in the core where, because of all the pressure from the gravity pulling inward, you've got atoms of hydrogen being compressed together into atoms of helium. And then that process releases photons of gamma radiation. And then those photons bounce around inside the star and they eventually make their way out to the outside of the star and then out into space. And we see that as the light from the star. But that process of those photons inside the star push against the gravity that's pulling it inward. And so for massive stars, they generate a lot more fusion in their core, they generate a lot more radiation inside of them, and they can be bigger. And then you get these interesting situations like a red giant, where the future of our sun again, where you've got this situation where it's producing a lot more radiation, and so it makes the star get a lot bigger. It actually makes it cool down from its visual temperature because it's gotten so much bigger and more spread out. And other situations where stars could be smaller, like a red dwarf star. So really, every star that you ever see is in this perfect balance. Gravity pulling inward, light pushing outward, and it is as big as it needs to be. Philip Moore. If we plan on mining asteroids in the near future, how are we planning on returning the materials back to Earth? Will we do it bit by bit, or will we just slam large payloads of materials into the ocean and figure out how to recover them? Well, I want to take issue with your assumption that we will want to bring any of that material home. I think it's entirely possible that we would want to bring a fraction of the material that we send to space back home to Earth. You're going to want to use it to build space stations and spaceships and space colonies and space bases and space farms and space power collecting facilities and space manufacturing centers. That all of that stuff is going to be best used out in space because it's so difficult to take stuff from Earth's gravity well out into space. But if you did want to return some of that stuff back to home, you would probably want to return it in the case of manufactured goods. You want to build a bunch of smartphones out in space and then return them all in some spaceship that is returning back to Earth after having delivered a cargo. There's some other ideas as well. I know Peter Diamandis from the X Prize has said that you could actually take, say, platinum and create a thread of platinum, like a big cotton ball, but made of platinum, and then you could just drop it into the atmosphere and its shape would slow it down and it would be able to pass through the atmosphere relatively unharmed. As you can imagine, there's facilities out in space that prepare some of the heavier metals that we want for returning back to Earth. And that'd be a very sort of expensive, very windfall if it landed in the wrong area. So I can imagine people trying to figure out ways to bring stuff back to Earth, but I think the vast majority of it, they're going to just want to keep it out in space where it belongs. Demir Ivanovic, love your new channel pick. Thanks a lot. Some of you have noticed, I'm using the pink artistic version of myself, and some of you, I hope, recognize the art style that comes from, and I apologize, Kurzgesagt. I helped with an episode on black holes several years ago, actually, and they were kind enough to draw a picture of me in that episode. And I'd always wanted to use that as my avatar, and I just had never gotten around to it. And so I asked Philip last time we were hanging out if I could use it. He was like, "Oh yeah, no problem, do it." And so I did. And so that's the one that I'm using. Of course, now it doesn't look quite like me, more hair. So it's pretty funny, but I love the picture, and I love that they drew me for one of their episodes, and I was really glad to be able to put it into this. So if you're wondering where that comes from, that's where it comes from. I'll put a link in the show notes to the actual episode. Jerry Ruprecht, bring back indoor. It's nice to see you pretending to be outside. Yeah, we've had like really bad weather, and things have been really busy around here, and we haven't had the time to sort of take the whole elaborate process out into the forest like we normally do, but hopefully the weather is now changing, it's getting a little better, and spring is here, and it's really nice out in the forest, so I guarantee we will be shooting more episodes out in the forest. So stay tuned, it'll happen, but right now I'm back in my office. So, Star Czar. If the universe is becoming less dense, shouldn't it become easier to traverse? The universe is becoming less dense over time, right? The leftover momentum from the Big Bang is expanding all of the galaxy clusters away from each other. Everywhere we look, galaxies are getting farther and farther away. But when you look at the actual stuff of space, the in-between areas in the solar system, in between stars, in between galaxies, it's mostly very, very empty. Just a couple of particles per cubic meter. And so you don't really experience a lot of friction when you are traveling through that. Now, we talked about this idea of an interstellar spacecraft that uses a magnetic sail to take advantage of that interstellar medium as a way to slow down. You expand this great big electromagnet, turn it on, it interacts with the particles in the interstellar medium, and that acts like a brake and allows your spacecraft, which was going, say, 5% the speed of light, to slow down. You can imagine over long enough periods of time, spacecraft will get worn down by all the particles that they bump into, but really, whether the universe is more dense or less dense, for practical purposes, it's not really going to change the speed and how difficult it is to move from place to place. What matters is the distance. And the farther things get apart, the farther you have to travel and the longer your journeys are going to have to take. And there are regions in even the observable universe that are falling over the cosmic horizon that we will never be able to reach. Even if we could go to the speed of light, we could not reach those distant galaxies, which kind of is sad to think there is this bubble around us that is getting smaller and smaller and smaller over time, of areas of things that we can actually reach as things fall over that cosmic horizon. I guess the bubble's still getting bigger, but things are going farther away than we can reach them. So no, we want the universe to be more dense, easier to get around in. Robbie Van. Does a light photon attract another light photon? Do they attract gravity on each other? It's a great question. And yeah, light photons will attract each other, because when you kind of go back to the way Einstein's theory of general relativity works, is that it's not about, gravity isn't things attracting each other like magnets. Gravity is a distortion of space-time. And so this is why light will be turned by a black hole or be turned by going around a distant galaxy, because it thinks it's following a straight line, but the mass of an object distorts space-time so that this stuff goes around a curve. And in fact, actual photons of light also can be converted. You can sort of do the math, the E equals mc squared, to figure out, if you have the energy of the photon, you can figure out the mass equivalent of those photons, and that will help you calculate how much space-time will distort because of the photons. And so two photons would actually distort space-time nearby to each other. And in fact, if you had enough photons, enough energy, you could create a black hole purely by their mass equivalent. So yeah, photons will cause gravity just in the way that mass will cause gravity. Sean Fugel. How can the universe keep expanding? It's been forever since it started. What's pushing the universe? There's two parts to what is causing the universe to expand. As we said, right now, we look in every direction and we see galaxies moving away from us. And if you went to any one of those galaxies, you looked in any direction, the galaxies would be moving away from them. And so what it really means is that every part of the universe is getting less dense over time. And so the question really is what's causing this? And you sort of can imagine something pushing, but everything is coasting. There was some initial condition that happened during the Big Bang that caused the universe before was incredibly dense, and now something, and we don't know, set off the momentum that has been carrying away all of these galaxies from each other ever since. It's just that there's nothing for them to run into. Right? As I mentioned earlier on, there's just a couple of particles per cubic meter. There's not enough friction. And so they are just going to keep on expanding and expanding away. Now, in 1998, astronomers were trying to measure just what is that rate to try and figure out, are the galaxies going to be gravitationally pulled back together again in some distant future. And what they found was not only are the galaxies not going to come together, but it seems to be accelerating. And so now, not only is it the momentum of this, whatever initial conditions happened with the Big Bang, but also on top of that, there is the acceleration that is causing by this mysterious dark energy force. And astronomers don't know what that is either. So momentum left over from the Big Bang and the acceleration due to dark energy. Chemdrive. Hey Fraser, would it be possible to build a ComSat network in solar orbit to facilitate higher bandwidth between Earth and robotic probes on Mars and beyond? You could definitely put a satellite network into space, maybe at say the L2 Lagrange point, and there would be a bunch of advantages to that, to communicating with other places in the solar system. But the main advantage, the thing that you want, is just raw dish size. You want a really big dish. People always want to talk about how they can communicate with the Voyager probes, even though they've left the solar system and the distance to New Horizons, and they're always so amazed, and they go, why can't I get a cell phone call? Well, if you're willing to carry around a 90-meter radio dish in your pocket, then you can make sure you'll always have a radio cell signal. So that is what's doing the heavy lifting, is a gigantic radio dish. And so trying to launch a 90-meter radio dish into space would be very difficult. Radio actually passes very well through the atmosphere, so there wouldn't be a lot of advantages to putting that radio dish out into space, apart from you wouldn't have to wait for the Earth to turn so that your dish would be able to have its target in the field of view. But then this is why NASA has the Deep Space Network. They have radio receivers at 3 points on the planet, so that no matter how the Earth is turned, one of their series of radio dishes can always see every part of the universe. And so that's how they do it. So I can imagine in the future there will be more infrastructure. The transmitters are interesting. Having things bounce from place to place would be great. big dishes on other worlds would be really useful as well. So I think over time we'll get more infrastructure on other worlds, and that will facilitate communication. But for now, I think just really big radio dishes would be what most NASA would love. Sebastian Gansey. If we use the same method of combining telescopes to observe exoplanets, what would we see? So this is based on the photograph of the black hole that we reported on last week, and I got a bunch of questions from people about, can't we use this network of telescopes to look at other stuff that would be really interesting? And the answer is no. The problem is that the Event Horizon Telescope is a radio telescope, so it's designed to look at objects which are emitting photons in the radio part of the electromagnetic spectrum. You could, specifically 1.2 millimeter wavelength. And to observe an exoplanet, like a planet like Earth, isn't putting out a lot. Well, I guess Earth is putting out radio waves, but your regular exoplanet isn't putting out a lot of radio waves in that kind of spectrum. And so you wouldn't really get a lot of really great views from this kind of telescope. You would want to use a telescope that is in a different wavelength, like visible or infrared. And there are capabilities to merge multiple telescopes together. It's this technique called interferometry. And I'm planning to do an episode on interferometry at some point. It's a very complicated subject, so I want to make sure I do it right. But the gist is that you can take even visible light telescopes, and you can hook up 4 of them, like the Very Large Telescope, and they can act like one telescope. And not just one telescope with the combined light gathering power of each of the telescopes, but actually a telescope that is as big as the sides of the telescopes, however far apart they are. The wider you can push those telescopes apart, the bigger a telescope they act like. And that is because of interferometry. But you have to be able to line up the wavelengths perfectly to the individual 100th or 800ths of a nanometer, which is really tough. They were able to do the Event Horizon Telescope because they just used really accurate clocks, gathered all the data, lined them up on computer, and they were able to produce that image. But with Visible Light Telescope, can you imagine trying to make sure you got to the exact right hundreds of a nanometer? That'd be really tough. So you're going to see over time more and more telescopes act as interferometers, multiple telescopes working like one. But it's, the farther up the electromagnetic spectrum you go, the harder it is to do. But like I said, I will do an episode on interferometry and give you the whole download on it, because it's an amazing technology, and it's given us some of the most amazing views that we've ever had. It's just harder and harder and harder if you're going to use visible infrared as opposed to radio waves. Leukemania. Are they going to try to image the supermassive black hole at the center of M31, or all of the galaxies in our local group for that matter? When James Webb gets launched and activated, will that be of any help in gathering these types of images? So that was the other main question that I got a bunch of, which is why are they going after all of these other galaxies as well? M31, the Andromeda Galaxy, the one that is rushing towards us right now, that supermassive black hole is 100 million times the mass of the Sun, while the one that's in the Milky Way is only 4.1 million times the mass of the Sun. So it's definitely a much bigger one, but the problem is that it is also a lot farther. It is 2.5 million light years away, while the one that's inside the galaxy is only 25,000 light years away. So what is that, 100 times as far away? Much farther, right? And what was the sort of the fluke of luck is with M87, the one they took the picture, it is vastly farther away, 55 million light years away, but it is gigantic, 6+ billion times the mass of the Sun. And so on the sky, when you if you just look in the sky and look for the big black holes, the one at the heart of the Milky Way is the biggest visually from our perspective, and then the one at M87 is the second biggest. But based on their success with M87, I really wouldn't be surprised if they then turn their telescope on other targets and start taking lots more pictures of whatever they can reach, and then just see if they can learn any insights about these various supermassive black holes. And it might be that the one at M31 is right within the limits of what is possible. So I wouldn't be surprised in the next couple of years to see more images, more attempts, as well as, of course, the one that's in the Milky Way. I can't wait. Roberts Leyes Myers. Love your videos. My question, where is the border when quantum physics transforms into macrophysics, and how does it happen? For example, atoms behave like quantum objects and exist as probabilities, but when they combine in molecules, then this and other quantum effects suddenly disappears. But how and why? Thank you for your great work and good luck. All right, that's an awesome question and way beyond my pay grade. So I have brought in a ringer, Dr. Sabine Hossenfelder. She wrote the book Lost in Math and covers all kinds of stuff about the cutting edge of quantum mechanics and the search for more particles with the Large Hadron Collider and why this has been so difficult. And I figured she was the perfect person to answer this question. And not only that, she has her own YouTube channel now with a bunch of videos. So you should definitely go and subscribe to her work and follow it from there. So take it away, Sabine.
This is a wonderful question. It is a wonderful question because I often hear that quantum mechanics is a theory for the short distances. But really that is not correct. There is nothing in the theory of quantum mechanics that says it is good only for small things. So why then do we not see quantum effects in large objects? One thing to keep in mind here is that we do see quantum effects for large objects like molecules, tables, planets and so on, because without quantum effects, matter would not be stable to begin with. Indeed, this was a big headache for physicists around the turn of the century. If you think that atoms are basically tiny solar systems with electrons circling around the nucleus, then the electrons should lose energy by radiation and they would spiral into the nucleus and, well, then there wouldn't be any atoms. It is quantum mechanics that prevents this from happening. And there are other quantum effects that we can't see on large scales, like, for example, the spectrum of thermal radiation. It only comes out correctly with quantum effects. Chad recently wrote a wonderful book about this, which is called Breakfast with Einstein, and in this book he has some more examples. But I will admit that this is not the typical quantum behavior that you may have had in mind, as with it being spooky and strange and so on. So where does that go? That too does not really go away for long distances or large systems, but it very quickly becomes very difficult to observe. It is not impossible. For example, Anton Zeilinger's group has created entangled photons that were separated by more than 100 kilometers. So that's a true quantum effect on really large scales. Other groups have managed to bring up to 1 million atoms into a Bose-Einstein condensate, which has quantum properties throughout. That's not exactly large, but not single particles either. But the problem is that these typical quantum effects, as with entanglement and being into places at once and so on, they are very fragile. They get destroyed easily and already by very weak interactions, for example with the cosmic microwave background. This is also why quantum computing is so hard to make a reality and why those quantum computers have to be cooled and be kept well isolated. That's because otherwise the quantum behavior would fade away quickly in a process that is called decoherence. Decoherence is basically the reason why we do not normally observe the typical quantum behavior in our daily life. Thanks for a great question.
All right. Again, thank you so much, Dr. Hossenfelder, for covering that question. That was amazing. I really appreciate it. As always, if you're watching these videos and questions pop into your brain, just take a moment, write them down. I'll gather them up and I will answer them here. I'll see you next week.